Was that you?
Yeah. What? Yeah.
Well, then you said that.
It's like two brothers and see what you get something like completely wrong. And it's like, what's the album? Dog. That's a good question. I think it was like. Oh, they want to go.
Wondering how to say.
Yeah.
Are you ready?
Yeah.
How's everyone feeling?
Better on the homework.
Okay, how many people did the homework today?
No,
How many people started on Tuesday?
no. Third, today is Friday.
Yeah, how many people did it today? How many people started last Tuesday?
Oh,
I'm trying to see if we should add an extra help session. I got
Alright.
messages near the end of the day yesterday,
Oh, I do a help session like on Mondays.
Yeah.
Yes.
That'd be hard.
but here's my problem with this. If you're putting it off for 5 days, then you're not gonna come on Tuesday when I already have a help session, or Wednesday right after I sign it. See my problem?
Yeah.
I'm trying to encourage you to do it as soon as you get it.
Mhm.
But I think naturally we have this like feeling like, well, it's not due till Tuesday, so I won't do it till Tuesday. Right? That's just sort of a natural human response. I'm not saying I'm better at this, right? Like if I have a proposal to turn in, it's getting turned in exactly at the deadline, right?
Yeah.
It's not getting turned in an hour beforehand.
Mhm.
But we need to stay on time, right? Because otherwise we're just necessarily gonna be falling behind, not understanding what I'm saying during class. Okay. So my instinct is not to give you a Monday session, but maybe to consider a Friday session.
Okay.
What time is it?
I have to send another doodle poll. I think a lot of people have constraints, right? Most people are taking the class. Generally speaking, I will be very vague on Mondays. If I even answer.
Friday.
No, Mondays. Mondays.
I thought you just said Friday.
No. I'm saying like, if you send me a message on Monday, right, I'm doing a lot of other things too. So
Oh.
I won't have like a lot of response to give you on a Monday. How did people feel about this homework?
I definitely felt better about it.
Okay,
Like, I feel like I was able to understand and justify the reasoning for every action that I did better than I did before.
okay. Is the idea of using Ampere's law and Gauss's law, is that kicking back into
Yeah,
your memory?
Yeah.
For 2 people? 3 people? 4 people? Yeah, I already got you. Okay. Okay. We start the brain off with the problem that we didn't finish. Infinite cylinder.
Oh, yeah, no.
This is a really good pen. Okay. Don't have fun, right? All right. What's this one? What were we talking about?
We wanted to find the B field inside and outside of this.
E field. Okay, so this is infinitely long, so that goes, well, that's a really good infinity.
Mhm.
Okay, and we want B. How do we do this? How do we start? What do we even have to consider?
Ampere's law.
Okay, Ampere's law, we could certainly do that. That would be something like B equals,
Oh,
what's that?
Mu naught H plus M. Oh, we're using it.
Okay, well.
Oh, we're
Yeah,
using
or
F as well.
dot DL.
S,
That's, yeah,
that's not S,
the interval,
integral, okay. Dot,
dot DL
DL,
equals.
I don't know any of this, you have to tell me, right? I just put B up,
Mu naught, I enclose.
you not. Okay, so now we have a problem.
Well, you know.
Not quite, not quite, it's not immediately obvious what I is, right? Yeah. Is there I?
Sure.
Yes, because there's a magnetization.
Cause there's a what?
Magnetization.
Yeah, so there's a magnetic polarizability in this material, right? That dipole moment is uniform up. So then we have to figure out what these are. How do I do that?
Filled up at the top.
And
Yeah, we can look at the bound volume, current and surface current.
There's no top.
Yeah, there's no tops.
Yeah,
This is why the only major difference between this and a bar magnet is the fact that there's no tops. The bar magnet do have a uniform seemingly magnetic dipole moment, and yet there's no currents in it, really.
Mhm.
Right, you're not running the current through it, and it has magnetization.
Mhm.
But that won't be the case here. I spent a long time looking at this, and I was like, what's going on? And then I remember the word infinite, that's why I wrote it at the top here. Okay. So how do we think about J in the context of bound current? What's that?
Are you asking?
What was the first thing you said? No, you're right. But what's the first thing you said?
Not L, it's not L, I don't think. Upside down.
Great.
triangle,
Yeah, that's Del.
cross, like,
And that's what?
zero.
Good.
It's not-
What?
No,
Oh, that's anyways. Very good.
I get the.
And this one?
That one would be.
M cross N.
Okay.
No one is not.
And this one is not zero.
Mhm.
Okay, and so I could jump ahead here. What would be the outside?
Zero.
Correct. Does everyone see that or are they just guessing?
Wait.
There's no M.
There's no magnetic polarization. Is that right?
Oh,
Good.
I thought it would be like the magnetic field of like a wire outside.
Right, so that would be fair if there was current running through this
Oh,
wire,
there was, okay.
right? But right now, what we're looking at is let's just take an infinitely long wire. And remember, infinitely long is kind of a joke, right?
Mhm.
Because if we zoom in close enough, everything will look infinitely long. So if I just have a really, really long wire, that will have these same properties. So now we don't run any current through it. Right? Do we have an expectation that there would be B?
No,
No, not really.
okay.
Long enough bar magnet wouldn't appear to have a magnetic field. Right? But if I turn it on or I go inside, then it will look different. Now turn it on is not the right word, you know what I mean? Okay, so what happens if I look inside the material? That's what? That's where it's funky, right?
See a little bit.
It produces like a current.
What produces a current?
The magnetic band produces a current.
Right. So the fact that there's an inherent magnetization in the material produces what kind of currents?
Amperian.
Bound currents, yeah. I mean, these are all the right way of saying it, but the specific word I want is bound. Because typically we've been thinking about in chapter 5, free currents. And now we'll think about bound currents, and then we'll realize that in everyday practice, you only measure the combination, right? You very rarely ever measure free currents. Okay? Just so it's up here too, we could also say B is written as a vector potential. What does that mean again?
It has direction.
Yes, but when I say vector potential, how do I, what's the formula?
Oh,
What? Del crossing, right?
Yeah.
Okay, and I might be able to look at this thing. What?
No.
And I might be able to look at this thing as the combination. Right, I claimed that this was true. J cross R hat over R squared D. Oh, let's do tau here. Plus. Right? Remember that a little while ago?
Yeah.
Okay. Unfortunately. Yeah, so this is the way that we would construct this idea, right? So we're talking about J enclosed, and we kind of just did that by looking at these two, knowing that one was 0, but in practice, this would be the real way that we do it. Right? Okay. So they're just having such a great time. They're clearly not taking this class. Yeah.
I do know that there's like another formula for finding magnetic fields and that involves H with the Ampere's law. Why do we use that one?
Great. I'm. It's almost like I paid you as a plant in the audience. Let's talk about chapter 5, right? And maybe this will get to your question, and maybe I just misunderstood the question, but it's actually a great segue into what we're about to talk about. So in chapter 5, we talked about free current, and that gave you B. And now we're bringing up this weird idea called bound current, and this weird thing called H. Right? Okay. So previously we talked about the current. We said J. Right? That's kind of sloppy. This should really be the total current. And it's the combination of the currents, correct? Which ones? Bound and free. Very good. Okay. There's another way to write this thing though, the bound currents. So I'm going to write this as J free plus del cross N. Okay. And I'm going to be a little sloppy here because my capitalizations look the same. That's not on purpose. That's just me trying. Okay. So this is really capital. Okay. You know, I'll fix it. This is bothering me.
Your name.
That helps me. All right. Remember what? Did you have to learn cursive?
Yeah, that's ridiculous.
Raise your hand if you learned cursive.
Yeah.
That's fucking crazy. Have you ever used cursive?
Only for my signature.
Yeah, and even that's scratched now.
Yeah, my signature is a chicken scratch. Okay. All right, so this is the idea, right? So here's the total J, and it's the result of the free current plus the magnetization. Right? Okay. So if I use Ampere's law, the definition that we had previously, we had something like del cross B is equal to mu naught J. So what's this one here? Yeah. Total E. And this one? Total J. Okay. I'm writing the same thing twice, that's fine. But let's write this a different way. Let's move this over. So we'll divide by mu naught. Okay, and that will allow us to break this J apart. Del cross B over mu naught is equal to JF. Right? From there. Plus del cross capital M. Okay. So now I might want to just have this thing. I can bring this one over, and I can do del cross both of them. Okay, so what is this thing then?
Oh, that's H.
What?
That's H.
That is the definition of it. Right? I could do something like, we call that thing H. Okay, so this is the field based on the free current in something that has magnetic polarizability, right? That is the definition of it. Generally speaking, we considered that there would be no internal structure to materials in chapter 5. And then we were like, well, that's nonsense, right? The cow isn't spherical. All cows have cylindrical body parts. And so this is the next approximation. That makes sense. Is that the question you were asking, or is that completely different?
I think that was the question.
Okay.
Well, it was basically saying there's a simpler way to do this, and this with every law.
Well, simpler, I don't know.
Well, it depends, it was just, at least there was like another way of doing it.
There is another way of doing it, yeah. There's usually multiple ways to do any of these problems, which is why I ask so specifically in your homework, say, why are you choosing what you're choosing? Right? You know, some people I saw, there was this one homework problem where everyone switched into polar coordinates. It's like, why? No justification for polar coordinates, right? It's fine, you can do it either way. You get the same exact answer. But you gotta tell me what you're doing, right? So the same thing's true here. You know, you could jump to this answer and you'd be like, yeah, I intuitively know that B is 0 because there's no magnetization outside. Great, awesome. How'd you get there? Right? Okay. So the thing that I just want to go back to, the thing that I'm going to continue to harp on is how this works in our mind, this mental model. You have a free current, okay, creates a B. The B causes an M, magnetic polarizability, and that modifies our B in a way we call H. The mental model makes sense? Anyone want to see the arrows, or you can?
You said that again.
Yeah, okay, all right. I'll write it. All right, we'll do this in order. Free current. Causes. B. Okay, that produces M. Okay. Modifies B, or something we would call okay. There is an example here about, think about a bar magnet. Okay, bar magnet not infinite. Has some magnetic polarization in it. Say it's a ferromagnet. So that's the first part. This is M. And you consider the B that it produces. Outside, it's like this kind of canonical dipolar magnet structure. B. And what is H then? Yeah, so this is the B picture. This is the M picture. What does the H look like? Same? Exactly the same in every way?
Only smaller. Because if M modifies B.
Because M modifies B. Okay, so it'll have this shape here on the outside, and on the inside it'll be modified by M. Right? So you just combine the two to get the view, right? This minus this equals this. That's the picture. Right? And inside it has a fun shape. Okay, we have two of them. This. Just modify the interior side. Okay. Okay. There's so much material here.
It modifies the outside only. Modify the outside.
This one here is modifying only the interior structure. I think it's a party. I don't know what they're doing.
It's a banquet every day.
Is it really?
No.
Uh, okay. So if you have magnetization and it's diamagnetic, okay, let's say you have some magnetic polarizability M, and it's either diamagnetic or paramagnetic. Does it produce its own B field? Raise your hand for producing its own B field.
I think it's,
Raise your hand for not producing its own B field.
wait, like instead it produces H or?
No, just asking, you have some material that's paramagnetic or diamagnetic. Does it create B?
In it makes them.
Right, so in a B field, it will affect the existing B field. But without an external B field, you don't get any. Right? That make sense or no? Okay. So a diamagnetic material, what would an example of that be?
Something with odd amount of electrons?
What's that?
Is it something with odd amount of like?
No, that's. I think it's right.
Like wood.
What?
Okay, they say wood as an example of diamond.
Yeah, let's just contrast it with the stuff that we know produces a B field. What stuff produces a B field? I may have drawn a picture on the board already.
Come back.
A magnet made of
Iron.
iron, a ferromagnetic material. Okay, so let's say a diamagnetic material or a paramagnetic material. Okay, these are pieces of metal which have the ability to be magnetized, but they don't carry intrinsic magnetization, right? They are not intrinsically producing magnetic fields. They will affect B fields once they're created. They're not just walking around being B fields, right? Okay, so here's a chair made of metal, right? If I place that into a magnetic field, that will affect the magnetic field. Okay. Reasonable or unreasonable? Okay. So usually these B fields for these two are sustained. I don't know if I can spell it. Sustained B by an external. That's not right, right?
I think it's right. External.
I literally don't know how to spell. B field. Okay. It's usually proportional. So you might be inclined to think that M is something like this. Okay. Might be thinking analogously. So P epsilon naught psi E like that. Like that. What think of that?
Yeah.
Yeah, because I wrote it, right? Or whatever. That makes sense. Reasonable? It's not the case. No.
Wrong.
Okay. It looks like this. Okay. Well, it's the same. Shut up, right? Okay, what's the difference?
There is a magnetization component,
What?
or there is a.
Permeability of roots.
It's you have like an additional term now.
What? You have an additional term inside of the H, yeah?
Yeah. So
Also posted on the. Like, where'd you get this from?
What?
where'd you get that?
Where'd you get that? How did I make this?
Yeah.
But like, you wrote no, that is.
No, I'm telling you what the magnetization,
Okay,
the inherent dipole magnetization is proportional to 8.
oh, okay.
Right, so for some material, this is the magnetic susceptibility of the material, right? So that could be 0. Something is not susceptible to magnetization, styrofoam. I don't know if that's actually 0, but assume styrofoam is not magnetizable. Okay, then this piece is 0, and it doesn't matter what H you put on it, you're not going to get any response from the material, right? Here we had a very similar idea. We said that the polarization vector of the object that's being polarized was the susceptibility to polarization times the electric field that you put on it. And the difference that I'm trying to show you here is that you would think maybe at first glance that this is how you would construct it. Well, it's just the B field that I place on it plus or times the susceptibility, the magnetic susceptibility. And I'm saying no. Because it's not the B field you place on it, it's the H you place on it. Okay? And the difference here has everything to do with the fact that the way that we write H is defined by free currents. This is why people get all hung up on which one is the quote unquote magnetic field. Okay? H is the one that you measure, generally, right? It's the free currents one. Here, you have some impact if the material was not polarizing. But if there's any ability for the material to be polarized in a magnetic field, that changes this. So this one here, this B that we've been using all along, is kind of hidden from us, from our real view. Does that make sense? Okay, this is the warning that I'm giving you. You can, of course, get between them. But physically speaking, H is the thing doing the work. Because, as I wrote over there, free current creates an imaginary B. It's not really imaginary, it has an impact. But then the impact it has is to induce M, which changes the original B. Make H. That process all coming together in sort of a story now. It was a bit of a journey. Okay. Another way of writing this. Well, I'm not gonna write it too many times. Let's talk about ferromagnetism. That's the fun, right? Like, okay, so what's ferromagnetism?
Fields that can keep their magnetic fields after leaving an internal magnetic field.
Right. So it's like the opposite of what I just said, right? Something that doesn't not diamagnetic. Okay, so ferromagnetism. Ferromagnetic material. How is the magnetic polarization compared to the B fields? What's that? Oh.
It's in the same direction.
It's in the same direction. That's the first part, right? And M is parallel to B. For diamagnetism, it's perpendicular. That's the di, and the para. Parallel.
Like different
What's that?
directions.
Well, yeah. Sorry. This is not perpendicular, but opposite parallel. Parallel, but negative parallel.
Okay.
That makes sense. Okay, let me just do that again here. Let's make sure that we have this properly. So this would be M minus B. The opposite. Oh God, I almost lost that B direction. And then this one is the same type. And which is the stronger of the two here?
Sure.
Sure.
Yeah.
Generally speaking, in an object. Where do they come from? Remember? Electrons, good. Both of them come from the electrons. Which one comes from which? Which two properties of the electron?
Valence electron? Oh.
Orbit.
Orbit, spin and orbit, right? So the fact that they're quote unquote spinning, not really real, well, that's fine. And then the fact that they're orbiting, which is a very real phenomenon. Okay. Spin and orbit. Make sense? And that's written down from you. I forget where it is, but it's, you know, this quantum mechanical formula for M, which is something like 2 parentheses L plus S. Okay. Okay. So in a ferromagnetic object, you have some material. Let's say you look at the wood on the desk in front of you, and every piece of this like grain you can think of as little groupings. So you have some material like this, and I zoom in into this region, and in this region, there's like these little quadrants. Now, this isn't exactly how they're structured, but it's a metal. So there is this like matrix-like structure. Okay. And they'll just like be whatever which way they want. Okay. Right. You have these little clusters, they all point in the same direction. Okay. They like to point in the same direction as their neighbors. So this is like the pure pressure. We were talking about trends and like following trends. So here, these people all, these dipole moments all point in the same direction because their neighbors point in the same direction. And here, they all point in the same direction because all of their neighbors point in the same direction. Okay, so we can coerce this material to have all of the magnetic dipoles point mostly in the same direction. Okay, how do you do that? Yeah, you apply some external magnetic field. Okay, so let's say we apply some external B. Okay, and then that'll start to align the dipoles. So the ones that are already aligned, they won't move, but all the rest of them will feel a force. Right? And that force will cause some of them to start to move, especially at the boundaries of the ones that are already aligned, and then they'll all start flipping. Okay. In a ferromagnetic material, there's not a simple relationship between B and H. Okay. The magnetic property itself depends on the history. So how magnetized the material is depends on what conditions it's been through. Right, you don't just grab a piece of like iron. You say, well, iron has a magnetization of 4. No, iron has a magnetization of whatever it has been subjected to. Whereas something like magnesium, right, which is a diamagnetic or I forget. What's not ferromagnetic has specific susceptibilities, right? Okay. You can get to a reasonably well-behaved state by like taking this object. Let's say we want to get it to a non-magnetic state. There's 3 different ways, but one of the ways that we could talk about, we have this hysteresis curve, which I think we're familiar with.
Yeah.
Okay, so we can get it back to the middle of that curve by changing the direction of the magnetic field back and forth. And what else would you have to do? Get rid of magnetization. What's that? I don't have access to heat. I only have my magnetic field. Can I use magnetic field to demagnetize my magnet?
Yeah.
I magnetize. So let's say I let someone in my lab. I don't have a lab. I let someone in my lab. They made a huge magnet. Now it's messing up everything in the lab because it's such a strong magnet. So I need to undo their work. Is it possible with just a magnet? No? Raise your hand for no's. Okay, so remember we have to think about the history. So let's make a hysteresis curve. Okay. So this will be the magnetic field that we apply to it, B. And then here is the magnetization. Yeah.
Was your question like, can you completely 100% like undo it or?
Tell us last time that can't happen.
We're gonna find out.
It's gonna-
Things never goes to work.
What's that?
So they can never go back to the order.
Well, here's what I said. What's that? So if I was taking a magnetic field and I went from here to here, and here to here, to here to here, then it never went through the origin, isn't that correct? So it started here, and it got magnetized, and then I changed the polarity, and it went like to here. There, and then I went over to this, and I went back. Okay, and then I said, well, now I can never get it back to zero. Just changing it back and forth and back and forth. Okay. So it's still true. But I'm going to claim now, if I look a little more carefully, there might be a way to remove the magnetization.
You go back to do like the original.
Well, doing the original method was going from 0 to some.
Yeah.
So we just rev it back in.
Sorry, say that again?
Do like half of it.
Do like half of it. So if I go not all the way to fully magnetizing it the other direction, but now if I go from full magnetization to like say half, and then half, and then half, and then half, right? Then some of those that are out here will not be fully magnetized, right? You'll only get to this region. And you'll create a hysteresis curve that instead of, well, let me just do this much more carefully with two colors. Okay. I'm going to show you the outside and then the inside. Okay. So this was the start. Not an artist. No one ever said it was an artist. Okay. And then this will be. Okay, now I'm going to bring it back through, but I'm going to use less magnetic field. Not that quick, but you get the idea. Yeah. Yes, yeah. Technically never fully back to zero, right? But zero is just like misaligned. What's that?
So it's like an infinite times once sort of
I don't know. Yeah. For this one here, we're just getting close enough that each of these, remember these little pieces in here, they can do whatever they want now. Okay? Because getting it to be magnetic with everything polarized in the same direction requires an external field pulling it all in one direction. And there's three ways to remove the magnetization. One is the way that we just said. We use the same technique that we magnetize it, but now we decrease the amount of the magnetic field each time, and that lets cells stay wherever they want to be with each process. Okay, there's two other ways. Heating. Yeah, that's the obvious one, right? Have you ever done that before?
No.
You like have a bunch of buckyballs, you're around a campfire, like a metal grate. You throw the magnets at the fire, like so it sticks to the grate, not in the fire. And you never done this?
No.
Okay, this is a unique story then. Okay. We were at my friend's house. He has like it's Colorado, so it's freezing cold. So you always have a fire on because trees are free. And so he has this like metal stove with the what is this thing called? The chimney, the metal chimney.
Yeah.
And we had like buckyballs, and we were throwing them to see how many buckyballs. You ever seen buckyballs?
Actually,
They're neodymium magnets, and they're circular. And they're what's that?
they make nice when
Yeah. They're
Oh,
very
okay.
strong.
Right?
It's like ours are like oval.
Yeah, they're like stones.
Yeah.
Oh, really?
They aren't like
Yeah.
spheres. They're actually like they look like rocks on the ground.
Yeah.
Okay, well, yeah, they sometimes look like this, right? And they make like little squares. You never seen this?
Oh, those.
Okay.
Oh.
The commercials.
They're
Yeah, they make like little 3D cubes.
Yeah.
It's going crazy. Everyone's trying to gaslight me here. But yeah, I'm not taking it. So we have these, right?
Yeah.
And I'm throwing them, or we're all throwing them at the stove because they attach. It's awesome, right?
Mhm.
So you try to see how high you can get it without it falling down.
Mhm.
And then like they're up there, we go do other things. We forget what we're doing. We come back. It's been like a few hours, and we start hearing this bang, 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 And I'm like, what the fuck is going on? So we think something's inside of the stove, like something has gotten in. And it's the buckyballs falling and hitting because they're demagnetized. It takes a while, but you can demagnetize them. So then we just had rocks. It was very annoying because we didn't have a large electromagnet to charge them up again. What's another way we could do? So what before we get to the third one? Yeah.
This is kind of off topic, but
Yeah.
like, what happens when you put it back on like a TV screen and it changes the color of it?
Yeah.
Depends on the type of
Like, think of like a CRT.
yeah, so
Yeah.
remember that the way that we project images has very different reasonings. So how does a CRT work?
I don't know, it's serious.
It sends like electrons.
Cathode ray tube.
Yeah, there you go.
Yeah, isn't it like? It's like a velocity selector thing.
Yeah, it's a velocity collector method. You're beaming it at the actual screen.
What are you saying? What is it?
Like electrons.
Yes.
Yeah.
Okay, so you hit basically what is essentially a phosphorus. Okay, and you hit that phosphorus with electrons. You go. Okay, and so when you add a magnet right at the very end, why does it get distorted?
Because you're messing with the electrons.
No, because the electrons are getting deflected.
Whoa, that's pretty. Wait, are those the TVs that like give you static on your camera?
Yes. Yeah, that's why. That snow that you see, that's real snow. And those are the ones with the long backs, right?
Yeah.
Oh.
Okay.
So the long backs.
Long backs, yeah. Okay, so what about plasmas?
That's just-
That's just what? No, plasma TVs.
Oh.
Sorry, not yes.
Stop right now. That's not fair.
Yeah.
Okay.
I mean, that was like the first generation of like flat screen,
Yeah.
TV, and they weren't even flat, they were still like round and shape.
Flat compared to like CRT? They had like 90s children have no idea. Okay. All right, let's go back to the idea. You have these magnets, you demagnetize them with heat. What actually happened?
You randomize these by.
Yeah, you randomized all these cells,
Mhm.
right? How did you randomize them?
With thermal solution.
With hot.
Thermal collision. Heat them up. Right? They move around in their cell matrices and they have some dipole moment, and those dipole moments are prone to changing. Is it fast?
No.
No, not in my story. It took hours. Okay. Yeah.
It goes like 760 Kelvin in the textbook. It's like, that's like the temperature, like once it reaches that temperature, it's like.
That's gonna be very material specific, but yeah.
Okay.
It's
Oh, I think that's for
70
ferro.
degrees Celsius.
Oh,
For iron, yeah. For ferro, yeah. Okay, what's the other way to do it?
You physically hit it?
Yes, that's the coolest one. So do you wanna explain this a little bit more, Jose?
You're like just hit the magnet, so basically you kind of rearrange the molecule for that times where
Yeah,
it takes up the magnetism.
this is insane, right? So you drop a neodymium magnet from a large enough height and it hits the concrete, no longer magnetic. Yeah.
Would your guess is for the other way, would another way being like, put in an electromagnet and just like move it around so that all of them kind of get mixed up?
That's the same as this, right?
But now it's alternating between one side and one side.
Oh,
I guess.
he's arguing that if you just move it in a random direction, like while it's in there,
Run.
they get so random.
So, okay, remember how we have to think about this, right? Because polarization, right, is always along one axis. So you can't have multiple polarization, right? Like
What a
can't.
field is.
You mostly have, let's say if you have a little bit on this side, a little bit on this side, then it's really long that side. Right? Because it doesn't matter what the orientation of the material is. You have it some three-dimensional. So we simplify this in most contexts as being parallel or anti-parallel. Right? Because otherwise you just reorient your coordinate system. Okay, so your idea is this, right? Because we don't really have, when we create magnetic fields, they are mostly created with big electric.
Are you able to do a thing where if you like a big magnet and you want to unmagnetize it, you just like go and just get little sections and make them go in different directions?
With like what?
Just like a
Like other,
little
like-
field and just like. in different
Oh, like take a little electromagnet
And just like.
and like,
make different
and then-
size, right?
Yeah,
Wouldn't the big magnet then over?
If we just, when it's, yeah, it's the net, it's like, alter like a whole field or something.
I mean, so it's just gonna cost a lot of electricity, right? That's the major issue.
Expensive experiment.
So usually you wanna use like a bigger electromagnet to magnetize or unmagnetize a smaller electromagnet. It's really hard to induce that type of change on a small one. You can take your credit card, right? And most of you have like Macs or PCs that have the magnetic lid that closes. So if you really want to ruin someone's day, you take their credit card and you just run it back and forth along the edge of their screen at the very top where it clips, and you can demagnetize their credit card. Now, thankfully, lots of people have chips and tap at this point, so it's RFID. But that used to be like, don't keep your credit card in your pocket. Like,
Yeah.
not true anymore.
so when you slide a credit card, is the reader just reading how it's magnetized and that connects it to your
Yeah.
account?
Exactly. Yeah. Well, depends on where and what phones. But yeah, you can eat, those are so easily demagnetizable. Those are crap, right? So like, even if they get too hot, like you take your hotel key down to the water and you're like at the beach all day, the thing's boiling, now it's demagnetized. Yeah.
They're also doing.
Yes, they're also. We'll not talk about that because I'm trying not to go to jail today. Okay.
Until you like.
I mean, we're moving through this material fairly quickly, so I wanna, yeah.
So, with the ferromagnet, like you said, like if you drop it from behind a pipe, you can demagnetize it.
Yeah.
Can you do the same with a hammer?
Yeah, hitting something hard is the same, right?
Okay, yeah.
So that is kinetic manipulation of the molecules, right? So molecules can undergo rotation, they can undergo translation, they can undergo vibration. So when you are heating something, right, you usually are increasing, depending on the molecular structure. Let's say you have iron oxide, you have oxygen and iron, which are moving like this. And now you usually are going to give them rotation and vibration first with heat. You're not just going to move them because they're in a matrix, right? So as you rotate and heat up these molecules, right, that's how your microwave works to heat up the water molecules. It actually heats them both with this type of motion. The hydrogens are moving in, let's say this is the oxygen, they move in like this and they heat up the material, or they can rotate depending on what structure they're in. Okay. So generally speaking, that's like vibration rotation, but you can just hit them, right? And that shock propagating through the material will break that structure for like a second, right? And then they just orient however they want, not a second, you know what I mean?
Are people who think that you can use a microwave is just dumb?
Yes.
Okay.
I thought that was obvious.
So I'm not sure if like there's anything that actually is happening to.
No.
Inside.
No. So it's the same type of like, reasoning that like people say, oh, MSG is bad for you, right? So MSG is just, what is sodium chloride? Table salt, right? So anything that is too complicated to understand, right? Like a chemical structure. In America, we have a really hard problem with education, with very poor science education, and that has propagated all the way up. Or like even people think that science is a bad thing, right? Because it's inaccessible, because it has words that I don't understand, so therefore it must have evil intent. No, MSG is basically, right, something that's powder, just like table salt, you use it as a seasoning. Microwaves, it's new, it's dangerous. Oh no, chemtrails, right? Yeah, chemtrails. No, just because you don't understand it doesn't mean other people don't understand it, right? One of the things that we have to be very respectful of, though, is like how we engage with that, right? So your cell phone, right? If your cell phone up to your face gave you cancer, we would have this huge rise in cancer in the past 30 years because every child these days, right, has their phones stuck to their face. Right? But the reality is that we don't see that. And why is that? Because the Bluetooth technology that we use to communicate is non-ionizing. Okay, so if you had ultraviolet rays coming out of your phone, yes, everyone's face would not only be super tan, also be falling off from the cancer, right? So generally speaking, you're looking for whether or not the radiation, which is very poorly named, by the way, right? We probably shouldn't call microwave radiation because we didn't think of the ramifications of connotating gamma radiation and microwaves, right? That's not hard for people to connect those dots if you don't understand what radiation is. So yes, microwaves themselves, they do emit, they have radiometers, they emit microwaves, they heat your food up. But it doesn't have enough energy to mess up your DNA. So how do you get cancer? Is through DNA manipulation.
So is France banning the iPhone 12 is ridiculous. It's like, it says there's like
Radiation coming out.
too high of radiation coming out of it. Like that in itself, I thought was weird.
I don't know what that means. We can look at that when
Yeah.
we get to the radiation section,
Okay.
but it's likely either there's a manufacturing defect
Okay.
where like truly there is radiation coming out. I mean, there are components, right?
Yeah.
If you think about what makes a phone,
Yeah.
you are accelerating electrons too much, you can produce forms of radiation which are dangerous, right? But generally speaking, that's not happening, especially in technologies that are tried and true. Right? Think about a microwaves first invented in the 40s, 30s. Okay.
Sorry.
I mean, like, you're right.
Do we understand ferromagnetics?
Yes.
Okay, has everyone turned in the homework, by the way?
Yeah.
So, I know Giselle's online, so you're turning in your homeworks, here's what I'm looking for, because next week. All right, you know, I really wanna see, like, when we do this experiment of ungrading, which gives you a little bit more freedom to reinterpret your work, to turn it in again, to make sure that you're really understanding the material. There's also a trade-off, as I talked about, with, well, I don't really wanna do it. And I can get away with just doing the bare minimum, or like, you know, half-ass it, because there's no like number at the top. So there's some latitude, and that's the feedback that I got when we did fluids together. So when I look at this homework, we're gonna decide whether or not we wanna do a test. And I will try to grade all of them before Thursday, so I'll tell you on Thursday whether or not we would have a test on the next Thursday. Otherwise, we'll be doing check-ins. If people have a preference for test versus check-ins, you can close your eyes. Everyone close your eyes, because I don't want you to like, you know, if you have this personal preference, I don't want you to be like, why'd you say that? But close your eyes,
No, God.
everyone, or raise your hand if you prefer test. Okay, raise your hand if you prefer check-in. Okay, raise your hand if you don't have a preference. Okay, interesting, all right. Okay. Maybe we'll just do it, you know, by people's volition.
Oh, God.
Oh, you can just opt.
What?
Oh.
You can opt into the test if you want.
Come on.
Take a look at it.
Can you look at the test? No, it would be.
Like, can we look at the test? We'll be like, okay.
No, I'm not feeling this thing.
So what I think we'll do, you know, depending on how this goes, if the homeworks mostly seem like people are understanding it, they're doing the whole problem, they're writing how they did the problem, we will do a check-in with an in-person problem. If that's not the case, if it feels like most people aren't really keeping themselves like on the track and they need a test right now in order to like make sure that they're studying, then everyone will do a test next Thursday. Okay. Because there's enough folks in here that don't mind doing the test. Okay, and if you need accommodations, let me know, obviously would be exempt from that. Okay. Okay. So this is the end of like the ferromagnetic part, and now we're gonna start talking about the last section of magnetostatics and matter. And then we'll be headed towards the direction of how does this all connect? And so that's what I'm gonna start talking about right now. Do people have any questions about how to do the B fields, the H fields, the connections between them? Before we move away from this? Okay, what is an H field?
It is how,
It's the real magnet.
It's the
like-
what?
It's the real magnet.
It's the weird magnetic field. I like that definition.
Not
okay.
weird, the real.
The real, oh, I like
what
weird.
we're at,
Either one is fine. Real and weird are the same.
but
It's
it's
like
like,
B and the effect of it.
It's B and the effect.
It's the-
Yeah. So the way that we like to think about it is that B. Is this the bad one? This is another one. Oh, no, this one. Okay, B creates
M,
M,
in the middle,
influences
B,
B.
and the final output is B.
If the textbooks are, it says auxiliary field, is that B?
That's the.
H.
Cause they have.
Oh, yeah.
But this is like so contentious that it's not even worth engaging on. Right? Generally speaking, what do we want to know? Well, we want to measure the magnetic field in real life. That's almost always
H,
H. Right? Except for when we get to space. Okay, when we see, let's take the magnetic field of the sun. Okay. Well, that's B, because there's nothing in between us and the sun. There's a little bit of plastic, but not very much, right?
Would H be the induced field also? Cause I feel like I see induced and auxiliary a lot.
well, is there anything to induce, in space in H? But it doesn't.
That makes it sound like H is just the magnetic field plus the effect of like stuff like a dielectric.
Yeah, that's exactly what it is.
is.
So generally speaking, what you measure in a lab is always H. Right? H is the result of the free current.
Does that mean that B is H when there's no, it like freezes
M.
in a vacuum?
That's exactly what he said. So,
Yeah, so we can think about this in two ways, right? So sort of like our ideal spherical cow, right? Like B would be this context where we didn't have stuff that could be magnetized. But in reality, almost everything is kind of magnetized. Right? So that's the difference here. Is that we lived in this like fun, fancy world where B's were a thing. They're not really a thing. It's mostly H. Right? Because of this interaction with M. Make sense?
So each is just the relationship between the two? Or
What do you mean by it's just the relationship between the two?
like what is H a quantity of how B is affecting M and like the circular?
It's a combination of the two, right? Didn't we talk about the fact that, well, let's see if I can write it again here. Okay, I'll write this one more time and we'll just see it. Okay, so we said something along the lines of del cross B was equal to mu naught J. Right? Okay, this was the total B and this was the total J. So this piece here really is JF plus del cross M. So this thing here is JB. So there is some internal magnetization, magnetizability, so to speak, and that creates bound currents. So here, I can move this piece over here and I can say del cross B over mu naught minus M is JF. So here's the thing that we see. I turn on the light and current goes through the wire. That's this thing. This thing I don't really see that much. But now my wire suddenly has what I would call like a magnetic field. It's pulling another magnetic wire towards it. Right? That I can measure. I can measure the force between the two. So this is the thing H that exists in real life. Everyone gets that? Yeah. All right. So let's take a look at potentials and Maxwell's equation one more time. Okay. In electrostatics, we wrote something like del cross E equals in electrostatics. So we're gonna say
No spin.
what?
No spin.
No spin?
Yeah. Maybe like do del cross.
Yeah, another way, yeah, so no curl.
Yeah, curl.
Spin is not quite the same as curl, right? Spin maybe implies rotation,
Okay.
and this would be like a curvature. Okay. But this means that I can write E like this. Okay. That's called Helmholtz theory. Does this work if I have a changing magnetic field? Yeah, there's a slight modification we had to make, right? So that was electrostatics. So in real life, we have del cross E is what? Right. EB, ET, and I'm actually gonna put a little minus here. Okay, so that didn't work for a changing magnetic field, so I had to add this in. What does that mean for our potential? Right? Okay, so we still have something like B, which is del cross A. That's the vector potential. And this is due to the no dipole moment. Or sorry, no magnetic dipole law. Okay. What happens if we put that into Maxwell's equations? Okay, so let's put this piece here into here. So del cross E is equal to minus d dt of del cross A.
We did.
You say we did it? Yeah. Okay, not quite. Is this done? You seem to like it?
I'd be happy.
You'd be happy with that, okay. I'm not quite happy with this because it doesn't mean much. Yeah. Yeah, that's a good question. What's the A?
Wasn't it like kind of into like a magnetic?
What's that? Well, then lots of people talked over each other. Raise your hand. The magnetic potential. And specifically, this is the magnetic what kind of potential? Right. So this is the magnetic, oh God. Magnetic vector potential. Right, because the conversation we're about to have is how does all of this stuff that we've been talking about, materials and matter, stuff that's changing, okay, how is that all going to affect our potential laws? And whether there's conservation rules that we need to keep in mind. So electrostatics, we saw del cross E meant that I could simply do this. But now del cross E equals a change in the B. We saw that at the end of electrostatic last time. So we wrote B like this, we would distribute it in here. That's great, right? Now we fully understand it? Totally, no, no, I don't think so.
Oh, can we change the magnetic potential to be in terms of bound current?
Let's see if we can just distribute this a little bit. Okay. So can I put this inside of here?
Yes.
Yeah.
Let me ask this question. Watch.
That'd be completely.
So, because can this thing here be del cross dA dt?
Yeah, yeah.
Yes.
Oh, yeah, cool. And this is minus, right?
Mhm.
And this is del cross E. I'm sorry, I'm missing all of the vector signs, but you get it. You get it, okay. So now look, I got del and I got del. And if I move this over, what does it say? It says del cross both of them. Right? E plus dA dt equals 0. Ah, okay, that's what I wanted in the first place, right? Reasonable? So we have this vector potential up here. This is a slight modification. We have this thing here, which was from this piece here, del cross E, can be this because this property, right? If I put this in here, del cross the gradient of E, automatically 0, right? So now I see the same thing, del cross this thing, 0, so this thing must be that thing, the gradient of E. Right? Because if this is generally true, del cross whatever this is, it has to be the gradient, right? Because it's a potential, scalar potential, gradient. Correct or incorrect? Okay. So this piece here says that E plus del A is equal to minus and then I just do some fun little move around parts. E is minus del V minus okay, this is now electrodynamics.
The reason why the key could.
No, just for lettering. These are all partials. Well, this one probably is easy. I don't know, it's pretty similar. Okay. Yeah, I guess we'll just chug ahead. I don't know if I have time to finish this. What is Poisson's equation again? For electrodynamics?
Oh, the Laplacian is. Laplacian of.
Not the Laplacian.
The gradient squared.
Yeah, that would be the gradient squared with the Laplacian. What about this?
Oh. Okay.
Oh,
That one. That's what.
Right?
Now.
This is the first one.
yeah,
This is the first Poisson equation, right?
Oh.
And then the Laplacian is when we do two of these.
Hmm.
So I could say, take this thing here, right? And I could take the gradient of this thing. Gradient of this, gradient of that, gradient of this.
Oh, okay. Yeah.
The gradient of this is
Rho over epsilon.
rho over epsilon. Well, this thing, that's two gradients.
Squares. Yeah.
Okay, so this would be this first one. If I take the gradient of the whole thing. Okay. First one is rho over epsilon. Oh God. Good. The second one? The Laplacian, good. Committed to getting it. I love it. That's the commitment I want to see. Laplacian. Okay, and then this last one?
Derivative squares. Yeah, second derivative. But then you have other components.
What?
Oh.
Well, we did this a little bit earlier. Remember we had ddt out here and we had the gradient in here?
Uh-huh.
These things are commutative, right? We don't care which order we do them in.
Okay.
Okay. What? So here I have dA dt, and I just want to take the gradient of it. So I can either put it outside, but I'm gonna put it inside for reasons.
So partial, yeah.
Okay. Right? You love reasons, right? Okay, so it's cool. Okay, so now I have something that has the potentials, both potentials. I have the charge inside. Let's find an equation for J. Okay. We're gonna get through all this. What? Should we pause it here?
We're not gonna get into it.
Like for parts of your clip.
Like for part two, yeah, subscribe and like for part two. Okay, so let's leave it here because this is how we are connecting the potentials between the electric potential and the magnetic potential. But the place that we're headed is how we're going to eventually propagate light. Okay, because so far we haven't really talked at all about the field in which this material is moving through. We are all seeing right now. Is everyone mostly seeing if they have their eyes open? Something I know, it's okay. So when we think about the fluid dynamics, and I want you to maybe just ponder this over the next 2 days. Think about fluid dynamics, think about the way that I'm speaking to you right now. If I'm speaking to you, then you have to be able to hear me because there's air. So I'm basically pressing stuff here, and your ear cilia get, whatever, so you hear waves. You may see that in water too. You see waves move through the water. So of course, for a long time, before Michelson and Morley, they basically thought that all light must move through some medium. Right? That's not a dumb idea. We know now that it's a dumb idea, but at the time it was not a dumb idea. So they tried to measure the direction of that material. Okay. Yeah, lasers. Right.
Yeah.
So how do you run this experiment? How long does it take? Can I do it in one night? No, in fact, you can't do it in one night. They were really good at measuring the speed of light, super good at it. And they found something really fascinating. So they would measure the speed of light every day. Okay. No, but let's look at it. Okay. We happen to be going around the sun. Okay. So we're going around the sun like this. It's not every day just in case. Let's use an informed idea here. If I'm driving around quickly and there's wind, sometimes if I'm going in a circle, I'll go in the same direction as the wind, and sometimes I'll go in the opposite direction of the wind. Right? So if there's a luminous ether, like they claimed, right, in which the material in which light propagates, okay, sometimes you'll be going into the material in which light propagates, and sometimes you'll be going away from it. And so therefore the speed of light should change. That was the expectation. Now you all know what the result of the experiment is, but this is, look at the equinoxes. We just passed fall equinox. That's the best time to do the experiment. And you have to wait a full year in order to fall. I guess a half year. You have to compare the two, right? But you need to go all the way around in order to be able to see it. So this is one of the most famous null results in history. Because this basically said it doesn't matter which way you look, speed of light's the same. And so your biggest question, the one that I want you to think about for the next 2 days, is what the hell is causing these waves to propagate in the absence of any medium? Right? Okay, and then have a look at this. You won't have an intuitive sense for it, but this is where we're headed. You'll see a deep connection here between the potentials. Okay, anytime you see V, you see A in real life. Not in our, physics 2500 where we only have some electric cow, right?
Yeah.
All right. So in practice, there is a deep connection between these two fields, and that's the reason why we can see it all. Yeah.
Who's chapter 7?
I think this is chapter 8.
Yeah, electric bending.
Yeah, it might be 7. It might be 7. We are headed into 8. I think we'll do a little bit of the work there, and then we're gonna go right into radiation.
Okay, so what do you recommend to read inside? Like right now?
The whole
So you should definitely have to, touch base on Maxwell's equations, right? Why they don't work, right? And so maybe that is chapter 7. But yes, like we say at the beginning of every new section, go reread those sections that we forgot last semester before the summer, right? Okay.